not do it. Okay, so, well, sorry, just having a little technical issue. I think you guys have seen this photo before. So basically, the focus of my talk is how the municipality goes from keeping this frazzled discs uh, from turning into something like this, which is really disruptive and quite a big problem, both for the maintenance folks as well as for the people that live there and live in the neighborhood. Um, So I'm going to use the term icing here, and I kind of use that as a catch-all term for a bunch of different phenomena. Basically, we're talking about ice masses that grow by successive layers of freezing and water. Um, One thing that I want to stress is that here at the municipality, our icing flooding extends well beyond what we might experience in a typical year or even, in a decade period from precipitation flooding. And typically here we have two types of icings. We have stream icings and groundwater icings, and maybe a little bit different from some of the presentations that occurred earlier this morning. When I talk about stream icings, I'm talking about much smaller systems. I'm talking about the types of streams that you could probably wade across relatively easily. Um, and just early here, I want to distinguish maybe two different phenomena, two different mechanisms. Our stream ices are driven primarily by heat loss and turbulent flow, and that leads to blockage of conveyance and overbank flooding. And then we have groundwater icings, which is primarily driven by heat loss. From groundwater that's been exposed to the surface. And I really want to stress these for us are the type of things that can spread just amazingly extensively, well beyond what you might expect from these little trickles of groundwater. Why is that important to the municipality of Anchorage? Uh, I mentioned, in terms of the degree, our icing flooding is well beyond what we normally experience from precipitation flooding. Also, the frequency. There's an icing event somewhere in Anchorage every year, as opposed, we might go years without a significant precipitation flooding event. And in some cases, we have icing events in the same place every year, at the same time of year. It costs the municipality a lot of money, both in terms of property damage as well as the labor from response from municipal maintenance crews and that type of thing. In a lot of cases, some of the problems associated with these icing events can be minimized with a little bit of forethought. And like I mentioned earlier with that slide with the house being surrounded by ice, these are incredibly disruptive and distressing to the people involved. I was asked by, like an elderly woman, in her 80s and 90s who was living in an old homestead. She called and she was looking for advice whether she should chip the ice first and remove it out of her house that way, or whether or not she was better off letting it melt and then kind of dealing with the consequences of like water flooding. And so just kind of like a no-win situation. Here are pictures of two different types of icings, but just to give you an idea of the extent we're talking about, the one on the larger picture on the left is a groundwater icing, and the two right-hand pictures are overbank flooding from Peters Creek. Um, the earlier talks this morning focused a lot on kind of the dynamics and the physics involved with some ice formation. I just want to stress some points here that are important to keep in mind as I deliver the rest of my presentation. Maybe just some like ideas, concepts to have in mind. And that is that natural channels, just because of their geometry and some of the associated structure involved around them, they're generally conserve heat better and therefore more resistant to icing. Steeper gradient channels, some of the smaller streams we have here in Anchorage can create a lot of turbulent flow, which sort of propagates the frazzle formation that was talked about earlier. And then just another thing to have in mind, it's not always the case, but it can be the case that as we start to experience freezing temperatures, depending on what type of fall that we've had, we may be seeing our seasonal peak for stream flow. I mentioned earlier groundwater icings, that come from groundwater that is coming to the surface. Um, and For the most part, not entirely, but anthropogenic causes, anthropogenic influences really exacerbate and create these types of icings. And here are just some pictures of various groundwater icings in the municipality, and you can see it's, you know, spreads quite extensively. That lower right there was the Eklutna gravel pit. I think the first year of operation, and they kind of got into a groundwater thing that they weren't anticipating, and it started eating their equipment. Uh, Maybe just another point to make is that these groundwater icings, they are somewhat predictable. There are climatic and watershed scale level influences that sort of control where groundwater is likely to be discharging close to the surface. They're influenced by the weather. So for instance, if we have a cold fall with not a lot of snow, we're more likely to experience problems with groundwater icings, uh, as well as these things are influenced by land cover and land disturbance. Um, I wanted to show this here. I've mentioned vegetation influences on sort of mitigating groundwater icings and how naturally vegetated areas are more resistant generally to forming groundwater icings. And if you look down there on the bottom, you can kind of see like a little schematic of like how that occurs. I'm sure everyone's familiar here when, in the kind of late winter here where all the alder and all the brush has laid down flat. That vegetation kind of provides an insulated pocket to protect these small flows, to protect these things from being exposed to the atmosphere and freezing. What I'm kind of shown in these pictures here. So here in the upper right, you have a neighborhood, a newly constructed neighborhood that's recently been cleared of vegetation. And pre-development, you were looking at the type of environment that looked very similar to what's on the left, where you have indicators of shallow groundwater moving close to the surface with the Devil's Club there, and so you go from this very robust vegetative growth to essentially denuded slopes that are exposed to the atmosphere. Um, this is an icing. Well, this is a flooding event shown here, but also is associated with an icing that occurs after the construction of the ball fields close to Tudor and Elmore. If you had gone out pre-development, this was not a particularly wet area, though there was a lot of water that was moving kind of from the associated wetlands complex surrounding Campbell Creek. But as soon as the fill was put in the form of the ball fields, you had a disruption of groundwater flow, and that kind of stacked up gradient of the ball field fill, and you started to experience its flooding, and then every winter now there's kind of an icing that occurs here. One of the real problems that we have with groundwater icings, and I think maybe similar to some of the photos that were shown in the DOT presentation, one common place for groundwater icings to occur is along road ditches and road cuts, and that's basically where shallow groundwater inflow has been intercepted and is being brought to the surface. Quickly, just stream icings. This is as was talked about earlier this morning. You're in a situation here where you have like dynamic ice growth as opposed to thermal ice growth, and the real distinguishing feature and the thing that's kind of is interesting for folks to observe the first time they see it is where you have ice that's forming actually on the bottom of the creek rather on the surface of the water. I'm going to go through these slides fairly quickly in the interest of time, because I think this has been talked about before. But what I want to stress here is, as I go through these slides here, is that stream icings is a dynamic process that has kind of this evolution of ice formation and ice cover. And I think this is important because when I start to talk about some of the mitigation strategies that we follow, it's important to keep in mind that this is a dynamic process, and to some degree, letting that process to continue to its fruition is one of the way that these can be mitigated. So this just shows the process of frazzle formation and the creation of anchor ice that kind of progresses to the transport of frazzle and accumulation and the formation of ice dams. You start to build, I always think of it as something, in the extreme example that maybe looks like Mammoth Hot Springs and Yellowstone, where you have these ascending ice terraces with water flowing across them. Once that occurs, you start to develop like a quiescent flow environment behind the actual ice dams. And if that stage stays high, you can actually start to see development of a thermal ice cover, formation on the ice margins. And what's really important there is you're starting to see a different heat environment where you're not seeing the same cooling that you saw. You're not seeing the production of frazzle, and actually you're starting to develop an insulating cover that will prevent the formation of additional frazzle ice. And this is a very busy slide, and I'm not going to spend a lot of time on it. I basically just want to stress that this is kind of like a dynamic spatial temporal process where so if you go out to a particular area and you see frazzle accumulating, that involves things that are going on upstream. It's affecting things that are going on downstream. What you might see at one point of a stream is very different than what you might see if you travel upstream or downstream. And if you go back out to a place, a couple hours later, it's likely that you're going to see something going on a little different than what you saw earlier as that ice evolution process takes place. And this just shows the same thing in terms of anchor ice dam development, water stage rise. But what I want to point out on the right-hand side there is as this process occurs, between mechanical and thermal erosion, you see kind of like a best hydraulic cross-section developing for the passage of water. And this is the point where we likely start to see stage drop, we start to see ice cover development, we stop seeing overbank flooding, and this is the point where, when we're dealing with flooding, this is kind of the point where things start to get better. One of the things that we focus on when we address problems like this, and maybe in some of the other things we do as well, we try to make sure in our mitigation strategies we're actually identifying and communicating the actual problem. Everyone's sense of this when they first come to an icing, they see a flooding problem and they think it's a conveyance problem, it's a flow problem, it's a water problem, it's a volume problem. Often it's actually a heat problem and maybe being made worse or a maintenance problem as well. Usually it's not a conveyance problem. There's usually, in terms of the underlying conditions, there's usually aren't flow restrictions that aren't related to the accumulation of ice. Everyone's probably familiar with the fire triangle. Maybe a way to think about our strategy for mitigating icings is to think of icing flooding as like a ice flooding triangle. And the idea is that you have a lot of things that are going on, and if you attack any one of the legs of those triangles, it's likely that you're not going to experience a flooding problem that's disruptive to people and property. So again, sticking with that same kind of strategy, just making sure that you identify the real problem. Can't be stressed enough is everything that we can do in our land development processes to keep encroachments away is really helpful. Recognizing that the flooding that you're seeing at a particular location is being influenced by factors that are occurring upstream. And then quickly, just some like big picture thoughts on mitigation strategies. Is there a way to address the vegetation problems that are occurring? Is there an opportunity to provide some warm water inputs? We have a lot of perennial stormwater flows here. We haven't done a lot of it, but I suspect if we were maybe a little bit more strategic on how we had those inputs come in, we may be able to disrupt the formation of frazzle and lead to less accumulation of anchor ice and ice dams and the rest of it. Also, just one thing that tends to happen with development, and if you're familiar with Anchorage, you can think of lots of cases in Anchorage where development has led to long stretches of overdeveloped streams, which just create these just long, giant frazzle production stretches. One thing that we haven't done a lot of in Anchorage was talked about earlier, and keep in mind we're talking about smaller scale things. Uh, you know, the idea if we kind of strategically allow these dams and this backwater flooding to occur, if we could do more to, strategically place those so that it's occurring upstream of areas of concern, and stopping that production of frazzle and developing that insulating ice cover upstream of the areas that we're trying to protect. I think that that's an area where we probably could do more at the municipality than we have. One of the things, and we're really blessed at the municipality, we have some great maintenance crews that kind of get this, and attack these problems in a more considered thing rather than just kind of, when we get phone calls and we get phone calls from residents, we get phone calls from the mayor's office, everyone's looking for, action, and often that can lead to a bigger problem. Everyone always wants to get a piece of yellow equipment into the stream and remove as much of the ice as possible. And the problem with that is you're actually creating an environment that's probably going to propagate the freezing process and the production of frazzle. I like to use the analogy of, people are often confused after they've done days of work with yellow equipment to try and remove ice, and somehow this icing keeps happening. And I like to use the analogy of that's like removing the scab on a cut and somehow being surprised that it's still bleeding. One of the things that people kind of, homeowners often want to do is they want to remove all of the vegetation possible, because clearly it's the vegetation. They see the ice forming to these things and they're thinking, if I just remove all the vegetation, then this problem will go away. Well, the problem is you're also creating an environment that's more prone to icing. Having said that, there are times where, like I said, allowing icing to occur, the evolution of an ice cover to occur in particular locations and being strategic about that is really helpful. But there may be instances where removal of a particular tree or something like that is warranted just to relieve flooding and high water at a particular location. This is just a conceptual solution from our design criteria manual that looks at addressing groundwater flows, reintegrating those flows, capturing them, trying to get them subsurface, and having them conveyed in a channel that has more appropriate, thermal resistance, is resistant to heat loss. And that's a channel that would be deeper than it is wide. So sort of turn the rectangle on end, and so instead of having something that's wide and shallow, you have something that's deep and narrow. Often in some of our higher elevation roads and neighborhoods in Anchorage, we do have the problem with the roadways intercepting shallow groundwater flows. And this is a pretty common solution that's employed in areas of the hillside and in Eagle River, where the drainage ditches are filled with drain rock. And what that allows, it allows that those groundwater flows to be intercepted. They're conveyed in the ditches. They're protected from freezing, piling snow. It makes often what can happen is if this ditch were not lined with rock, the snow that's cast into it kind of disrupts that flow, both in terms of the structure and blocking it. And so this has been something that's has been very successful for us, and it can be used with or without an accompanying like a perf pipe subdrain in the bottom of the ditch. This is, again, just conceptual guidance that we have for improving road crossings. Again, there's a lot going on here, but maybe the things is looking at things like culvert material, using plastic, using insulated pipe as opposed to corrugated metal pipe, trying to address low flows, groundwater flows, low winter flows. Perhaps that's conveyed underground. We were involved with an icing at the Beach Lake ski trails in Chugiak, and a derivation of this was employed where the low water flows were captured and conveyed subsurface compared to what might be conveyed underneath the trail during like a higher flow season. I mentioned ice removal. Our guys, our maintenance folks have gotten really good at getting uh, doing selective ice removal. So kind of trying to create like a small channel that allows for the passage of water, that allows for a stage drop, but trying to preserve that protective ice cover so that it keeps that evolution of ice cover, the thermal ice cover that stops the production of frazzle, that kind of so that allows that to stops that process so that we're not continuously creating frazzle and more flooding problems. This is a fairly traditional approach to mitigating icing problems at crossings. This is just the use of thaw systems. These photos here show the new thaw system that was put in at the Chester Creek crossing on Arctic. Typically in Anchorage, these are mostly turn on, turn off, but they can be, accentuated, actuated at certain temperatures. We're talking about, heat trace, you know, self-controlled. The cable itself controls sort of the temperature based on the environment it's around. One of the limitations of them is you need to have power available. I don't know. One of the things we've questioned whether or not it would be possible to use photovoltaic power sources to do these. I suspect that might be difficult given the amps involved. But one of the limiting factors, like I said, is that you need to have electricity available to do this. One of the methods that's used a lot in the municipality traditionally is steam thawing. Our crew uses something they call a banjo, which is basically a circular fitting on the end of a steam hose, and they cut these kerfs into these icings. On the left here is a stream icing, and on the right are some groundwater icings, and the idea is that they're capturing that flow, they're getting it below the ice surface, they're thermally protecting it, and they're breaking, stopping that process of lamination where you have successive layers of water flowing across the ice that are feeding the growth of the groundwater icing. And I just want to, over on the left is something pretty creative that they did. They put steam jets welded them onto a bucket. And actually what they're doing there is trying to avoid disturbing the ice cover upstream of the bridge, but are using that excavator bucket to uh, put those steam jets underneath to try and keep an opening underneath the bridge there. Uh, this is kind of an extension of that, like a larger scale version of what they do with steam thawing. We had responded to a flooding event a number of years ago by Golden View Elementary, and we employed the use of a ditch witch to create channels that would capture the water that was flowing across the surface of the ice, causing the icing to spread, getting it back down below the surface, and kind of stopping things. And it actually worked really well. One of the things we noticed that made it easier, or did make it easier for us, is we actually knew where the stream channel was. And one of the things that we found was key is in order to get this to work correctly was making sure that we remove the slush from those ice channels that we created. I've mentioned a number of times how important it is to kind of let the natural process, the evolution of ice cover to occur. And I want to kind of like a case study of two different water bodies in Anchorage over the same time period back in 2014. This first set of pictures here is from Chester Creek, and you can see on day one, kind of at the end of the development of ice cover, no longer probably a lot of frazzle production, starting to have mechanical erosion, starting to have thermal erosion underneath the ice. You're at the point where stage is starting to drop. You come back 3 days later, we had a warm up. There's absolutely no ice left in the channel. Basically, all the ice has melted back beyond the boundaries of the bankful, the stream banks. So, and this is just another shot at Cheshire Creek, same time period, just a different spot. Day one is again where stage is starting to drop, and then day three is you've had this just warm up event and all the ice is gone. What's really interesting about this is this particular ice dam forms in the exact location every single year, plus or minus a foot. So it's pretty cool phenomena. Um, Moving on to another creek, uh, same set of days, maybe a little bit earlier on in the process in terms of day one at Rabbit Creek. But again, day three, the warm up has occurred, thermal erosion has occurred, stage drop has occurred, all the rest of that things. But what you'll notice here is that a lot of that accumulated frazzle has persisted, um, in the channel and as serves as a thermal cover and protects the stream flow. And if anyone knows the difference between these two creeks, Rabbit Creek is more or less natural, and Chester Creek has been highly modified because of development. And the interesting thing is what happened when it got cold again a couple days later. Chester Creek started the whole icing process all over again. Disruptive frazzle production, ice dam production, stage increase, overbank flooding. Everybody was all upset. And Rabbit Creek was completely fine. No other problems. Same thing with Peters Creek, any of the other more natural streams. They had developed a persistent channel that was uh, resistant to heat loss and protective flows, and prevented that whole evolution from starting over again. And then just another kind of case study here. This is that same picture that I showed at the beginning of my beginning of my talk. This is what was done to mitigate that. You have on the left here, you have a metal culvert, clearly not a lot of cover on it, absolutely no vegetation, this wide channel, just everything that you wouldn't want to do to be able to pass flows during the winter. And this is groundwater flow, not stream flow, but fairly perennial because of some slope cutting that was done upstream. And then you see kind of what it looks like finished. There's a new insulated culvert there. There's more cover. There's vegetation's been allowed to grow, and there is no ice here. And this was a neighborhood that was bad enough that during a period of time, they were not getting postal or UPS and FedEx deliveries during part of the winter because the icing was so bad. And this is just a shot from the plan set that was used for the project. And you can see here that the core feature is a channel that's thermally protected, with narrow width and depth and accompanying vegetation that's planted. And there is a larger channel there that's there to pass thawed season flows, larger flows, but these low winter flows that really feed these icings, that's protected by that lower channel in the middle. I think it's always important that we keep an open mind, and sometimes unconventional solutions will reveal themselves. If you look in the upper left-hand corner, upper left-hand picture, I responded to this as a illicit discharge complaint for streams. I pull up, I see this, and I'm thinking, oh my gosh, what are these people doing? I take a closer look, and I'm like wondering, wow, something's going on here that I'm not figuring out. I talked to the resident, and actually, this is something they came up with on their own. It works fantastically well. Because of some land use decisions here, lots of vegetation, bad channel geometry, they had an annual icing problem that developed in this area. And so what they had taken to doing was bridging the stream with some styrofoam board, and then weighting those boards down with bags of leaves. They would set this up in the fall. They set this up in the fall, and then it's fairly easy to clean up in the spring. And ever since they started doing this, they have had absolutely no problems with icings. I think I left a little time for questions. Like I mentioned a number of times here, this is like a dynamic process with a lot of different things going on in terms of ice formation. And on the left here is kind of later stage on Peters Creek, and you've had this overbank flooding, you had the stage rise, and you got this really like torturally sinuous channel developing in down the middle of it. The thalweg for the stream is nothing, not at all like that. It's relatively straight. It kind of meanders down the valley cross section. And then, the second picture on the right here is weeks later. And you can see that, active icing has stopped. And, that was the channel for the rest of the winter was this tortuously sinuous, like deep, narrow channel. So, any questions?
We have a comment in the chat from Janet Curran, and she says she wants to mention that Chester Creek receives more flow from groundwater than Rabbit or Peters Creek.
It does. It does. It receives a lot more groundwater flow, and that would you would think that might provide a little bit of warmth, and I suspect maybe in the natural state before it was altered, there was probably less icing that went on in Chester Creek, and um, I think with the amount of channel modification that's gone on, it actually creates a problem because it just actually it just produces like a constant source of water. Um, but for sure, they're very different flow environments and kind of what drives them. I was actually, and the only reason I say that is my sense of it is that Chester Creek would have had less problems because we just would have warmer groundwater flows, and it's just not the case. Anything else? I think that's it.
All right.